Alrighty, sorry I'm a couple of minutes late, and let's go ahead and get started. Today we're going to talk about op amps. And op amps is one of my actual favorite topics because it's one of those things to where once you know how to apply the rules of circuit analysis becomes, in my opinion, extraordinarily trivial. So the crux of the video that I uploaded yesterday was that there are really only two rules when dealing with an op amp circuit. So let me draw the schematic symbol for an op amp. Like so, so less crappy looking. So we have a non-inverting terminal that's denoted by the plus sign. And an inverting input terminal denoted by the minus sign. Let me call this instead of input. Oops, that was a mistake. Input, here's our minus sign. Input. So these are the three terminals of an op amp that we're concern ourselves with. The first rule of ideal op amp operation is that no current can flow into / out of the input terminals, which means this current has a value of 0 amps, and this current has a value of 0 amps. And our second rule is that no voltage drop can occur across the input terminals. Which means there's no voltage there, which if we label our voltage at our inverting input as V minus, so that's a voltage with respect to ground, and we label the voltage at our non-inverting input terminal, that's again a nodal voltage with respect to ground, op amp rule number 2 implies that voltage V plus has to be identical to the voltage V minus, which again, all of this was covered in the video. So today we're just going to work a few more examples to illustrate how those rules can be applied along with elementary circuit analysis techniques like Ohm's law, Kirchhoff's current law, and Kirchhoff's voltage law in order to figure out what's going on. And so I'm going to phrase these problems as if they were questions on the exam effectively. So let's say, for example, that I have the following circuit. That is correct. They will not be on exam until exam 3. So let's call this guy 6 volts, 2 kilo ohms, 8 kilo ohms for my feedback loop. Let's have a 10K. Um, 2K. Let's call this voltage V out. And let's call this guy up about 5 kilo ohms. Alrighty, so this is a reasonably complicated, at least looking, operational amplifier circuit, but we can still get through it just by using really our ideal op-amp rules and then a couple of simple observations, okay? So if we apply our first op-amp rule, we know that this current flowing into this node has to be equal to 0 amps, and similarly, this current flowing into the inverting input must also be 0 amps. That's op-amp rule number 1, just being applied. Always works that way, at least for a negative feedback circuit. We also know that the voltage drop between these 2 points in the circuit is 0. So if this voltage at this particular node is, with respect to ground, is my voltage at my non-inverting input terminal, then the voltage here at this node must be the same quantity. So V plus again has to exactly equal to V minus because of op-amp rule number 2. So our general process for finding the output voltage is going to be really 2 steps. So our first step is 99.9% of the time going to be figure out what the voltage V plus is. And then step 2 is to use this to find V out. Those are really the only 2 steps in solving pretty much every op-amp problem I can think of. If you had a cascaded op-amp circuit, meaning you would chain multiple op-amps together, you would just repeat this for each of the op-amps in the chain. It's actually pretty easy stuff. So let's start with step 1, figuring out what V plus, the voltage at the non-inverting input terminal, is. Does anybody have any idea how we might go about doing that? KCL, okay. Explain yourself. So you're suggesting that if I add this current and this current together and set them equal to 0, I will be able to solve for V plus. I agree. It's not the method that I would choose, but let's go through this and then we'll talk about the method that I would use. So what that gentleman suggested was that V plus divided by 8 kiloohms plus V plus minus 6 volts over 2 kiloohms is equal to 0 by applying Kirchhoff's current law at the non-inverting input terminal. So we can rearrange this guy slightly. We would say, let's see, we're going to have V plus multiplied by 1 over 8 kiloohm plus 1 over 2 kiloohms is equal to 6 volts divided by 2 kiloohms, which is 3 milliamps. And so from that, we have V plus is equal to 3 milliamps times, let's see, what's 1 in parallel with 8? 16 over 10, so 1.6. Let me. Now, some of you might be asking, well, where the heck is he getting this 8 kiloohms in parallel with 2 kiloohms bit? I'm not really considering that these resistors are in parallel, but I know that when I divide both sides by 1 over the sum of 1 over 8 kiloohms plus 1 over 2 kiloohms, that's the exact same thing as the parallel resistance of those two together, right? So what I'm saying is 1 over 1/8 plus 1/2 is the same as 8 times 2 over 8 plus 2, which I know to be true. So I'm not considering those resistors to be in parallel by any stretch of the imagination. It's just the math works out that I can treat them like parallel resistances to get my fundamental answer. Okay, so let's see. 3 times, again, 16 over 10. So 3 times 1.6 is going to be 4.8 volts. Could somebody verify that for me? Alrighty. So that is definitely one way to do it. Now let's talk about what I feel would be a slightly easier way to do it. I get the same result, not going to be terribly difficult. So I would argue that since we know, and this is effectively applying Kirchhoff's current law to make this thing behave like something else, all of the current leaving the 6-volt source has to circle around and flow down through that 8 kilo ohm resistor. So from the perspective of the 6-volt source, it sees a 2 kilo ohm resistor in parallel, or excuse me, in series with an 8 kilo ohm resistor. So I would argue that using voltage division is also a very, very easy way to figure out what that voltage is, right? So using voltage division, we would have V plus is equal to 6 volts multiplied by 8 kilo ohms over 8 kilo ohms plus 2 kilo ohms. So what is 6 times 0.8? Well, it's also 4.8 volts, right? Any method that you want to use to get B plus is probably correct as long as you're noting that there's no current branching off and flowing into the non-inverting input terminal. So really it's, 6 of one, half a dozen of the other, but to me, the voltage division method is faster because you can do it in one step. Alrighty, so now that we know what that voltage V minus is, we can again effectively apply Kirchhoff's current law. So I could say that this current, which I'll call I, has to be the exact same as this current, because the current flowing through the 10 kilo ohm resistor none of it can branch off and flow into the inverting terminal, right? And I could have just easily drawn my arrows the other way and said that the current flowing through the 5 kilo ohm resistor can't branch off, so all of it flows through the 10 kilo ohm resistor. I'm choosing the direction to the left here purely because my voltage V negative or V superscript minus has a positive value, right? If we apply op amp rule number 2, we know that that voltage is exactly equal to 4.8 volts. And so I know that there's a 4.8 volt drop over my 5 kilo ohm resistor, and the current should be flowing towards ground. That's literally the only reason I chose that direction. You could choose the other direction and everything would work out perfectly the same. So from this, we can then see that I is 4.8 volts over 5 kilo ohms, which is the same as V out minus 4.8 volts over 10 kilo ohms. Excuse me. And we could rearrange these guys and we would find then that, let's see, V out is going to be equal to 10 kilo ohms over 5 kilo ohms times, actually, I think this is gonna make my algebra dumb. So let me do this slightly different. So what's 4.8 volts over 5 kilo ohms? Let's start there. This will make things easier on me. So 4.8 volts divided by 5 kiloohms, 0.96 milliamps, right? So that's purely from just this guy right here. There's no unknowns or anything. I didn't have to do any algebra, just evaluating things. So from that, I can say that V out is 10 kiloohms times 0.96 milliamps plus 4.8 volts, just using algebra. So 0.96 times 10 plus 4.8 is 14.4 volts. All right. This problem looked a little complicated, but was fairly straightforward. Let's up the level of difficulty by a good amount here, and then I'm going to let you guys try to guide me through this problem. A lot more components going on. Let's call this guy 2 volts, 3K, 8K, 1K, 6K, 10K, 2 milliamps. So this is our circuit. This is similar to something I would put on your test if I were in a bad mood. It looks awfully busy, but really the analysis steps are going to be extraordinarily similar. So first thing, as per usual, I acknowledge that this current must be 0 amps. I acknowledge that this current must be 0 amps. And then I need to recognize that this voltage here, V plus, is going to be the exact same thing as this voltage here, V minus. So step one, how do we find what V plus is? Two milliamps times what? Times the 6 kiloohms. Exactly right. So that voltage V plus is a voltage with respect to ground. So just using Ohm's law, we can say easily that V plus is equal to 2 milliamps times 6 kiloohms must be 12 volts. So fairly straightforward. Anybody have any questions, comments, or concerns about that bit of circuit analysis there? All right, what are we going to do next? So that equals V minus. So our next step is effectively just going to be applying Kirchhoff's current law at that inverting input terminal, right? So what I'm suggesting, it's similar to what I did the last time, but it's going to be a little bit easier because we have so many branching paths. And so what I'm saying is this current plus this current plus this current have to equal 0. And that's going to relate our output voltage V out to known quantities so that we'll be able to solve for it. Does that make sense? All right. So what's the current flowing through the 1 kilo ohm resistor? Expressed in terms of my So is there a voltage right here? Yeah, no problem. Okay, so we're gonna have 12 volts divided by 1 kilo ohm. What is the current flowing to the left through the 3 kilo ohm resistor? Will it be 12 divided by 3? 12 minus 2 divided by 3. That looks terrible. White pen thingy. Alrighty, and what's the current flowing to the right through the 8 kilo ohm resistor? Well, and so I've thrown a little bit of a red herring in here, so I want to be clear. The 8 kilo ohm resistor and the 5 kilo ohm resistor are connected how? In series. So we could treat this as just a single 13 kilo ohm resistor and make our analysis a little bit easier. So that's something that you might see on some of the homework assignments where they just put 2 resistors in series literally just to trip you up. So make sure to look for simple things like that. All right, so with that in mind, what's the current flowing to the right through the now 13 kilo ohm equivalent resistance? $12 volts minus V out over 13 kilo ohms is equal to zero. One equation, one unknown, we can solve for V out. So let's see, numerical solver. Come on, calculator, this isn't that hard. I got, my pen would write correctly. 211.333 volts, but I want to double check that because that seems excessively large. I want to make sure I didn't type something in incorrectly. 12 over 1,000. So it's nope, 211.333 is correct. All righty. I'm not sure what else to do because, I mean, in my mind, this stuff is pretty straightforward once you apply the rules. I guess the only, let's screw around to do a cascaded op amp circuit. So 2 op amps chained into each other, just for the sake of it. This would actually be considered far more difficult than anything that you would expect to see on an exam, but it's still not going to be that particularly difficult. Alrighty, so now we have a circuit containing two op amps that are chained together. We can still apply our basic op amp rules. So we know that this is going to be 0 amps. This guy is also 0 amps. This guy is 0 amps. And this guy is 0 amps. I'm going to call this guy amplifier 1 and amplifier 2 so that I can delineate what we'll call V plus 1, V minus 1, V plus 2, and V minus 2, like so. So we're looking at the nodal voltages for the inverting and non-inverting input terminals for op amp 1 and op amp 2. So what is voltage present at the non-inverting input terminal of op amp 1? 0, because no current can flow through that resistor, so there's no voltage drop over it. So that 3 kilo ohm resistor is effectively grounded. While we're at it, what is the voltage present at the inverting input terminal, non-inverting input terminal of op amp number 2? It's also 0. It's directly connected to ground. And just for the sake of argument, we'll call that V2 minus, and we'll call this V1 minus. I'm going to change something ever so slightly here, or not even slightly. Let's call this guy Vx. So this is the voltage at the output node of op amp 1, okay, with respect to ground. So if we wrote a Kirchhoff's current law equation and said that this current plus this current is equal to 0, we would be able to determine what that voltage Vx is, despite the fact that the other operational amplifier is connected to it. That's one of the beautiful things about an op amp, is that the voltage present at the output pin of one op amp isn't really dependent on what you load that op amp with. So what I mean by that, if we look back at these previous examples, so this guy has the output voltage over an open circuit terminal, whereas this guy had an output voltage over the 2 kilo ohm resistor, but we didn't in any way, shape, or form actually change the way we worked the problem out. And this first guy, that 2 kilo ohm resistor right here, never even showed up in a single one of our equations, right? So what we're loading the op amp with doesn't particularly matter. So coming back down to this guy, we could see that V1 minus 0 volts. So we would have 0 minus 4 volts divided by 2 kilo ohms minus Vx over 3 kilo ohms is equal to 0. Oh goodness, what the heck is happening there? And so from this, we could solve for Vx, and it will be -6 volts, if I'm not mistaken. You guys can verify that. If we apply Kirchhoff's current law, then at op amp number 2, we're going to have sorry, that should be 2 minus, not -2. V2 minus, which is 0, minus Vx, which is -6. So 0 minus -6 is +6 volts divided by 5 kilo ohms minus V out over 15 kilo ohms, sorry, is equal to 0, which would then give us V out is equal to, so we can cascade these guys together and it really doesn't increase the level of difficulty of the circuits, in my opinion, at all, because we can isolate them into easily digestible single stage amplifier blocks, where the output of this first stage is just looking like the input of the second stage, right? And so what I mean by that is we treated this second stage as if we had sliced this guy off and applied -6 volts at this terminal. Everything that happened to the left of that line, other than the fact that the output voltage was -6 volts, in no way, shape, or form influenced the behavior of the second stage. Similarly, everything to the right of the line didn't influence how the first stage was working. So, I don't know what else to do. This stuff is, I think, fairly straightforward. So do you guys have any questions about anything? Yes, sir. Yeah, on the exams, if you look on the old exam 3s or whatever, the only thing I ever ask is what's the voltage present at either the inverting input terminal or the non-inverting input terminal. And if you can solve for one, you get the other. Solve for V plus, and V minus has to be equal to that. And then I'll ask for what the output voltage is. That's it. In circuits 2, I start getting a little bit more wild asking things because we're not dealing with simple negative feedback circuits. But the only really thing that I might ask, even of a circuits 2 student, so, specifically an electrical engineering major, might be, well, what's the current that's leaving the output terminal of the op amp? And we can figure that out pretty easily just using Kirchhoff's current law again. So for instance, if I wanted to know what this current is, let's call it I op1, it would simply be the sum of this current, which is easily determined, plus this current, which we can also tell easily because we know how to find all the voltages. Op amps, especially negative feedback op amps, are probably one of the easiest topics that we'll see in this class, because it's just applying those two rules and then using Ohm's law, KCL, and KVL at the most. If you want to, we can go through and look at some of the homework problems, but they're honestly significantly easier than what we just worked out. So. Let's see. Why did it fail? It's automatically got my password saved. Oh, that's it. Thank you. It doesn't work because this isn't statics. Thank you very much. Sure. It's going to start with Thevenin and Norton equivalent circuits and go all the way through transient analysis. So that would be lectures 9 through 15, where lecture 15 kind of didn't exist. We did the lab because there really wasn't much else to talk about. Old tests and in-class assignment problems, by far. The homework problems on those particular ones aren't too different than what I would ask on the exams, but yeah, I mean, old tests and in-class assignments are literally problems that I have created with the expectation that you guys know how to solve them. And I'm the guy stuck making the tests again. So working the problems that I assign seems like a good idea. Yep. So let me share the screen for the web work stuff. So for this problem, I can't write on the screen, but we could actually pretty much look at this thing and determine what the output voltage is. So what I mean by that, what's the voltage present at the non-inverting input terminal? 0 volts, okay. Where is all of that current IS going to flow? Through the resistor. So what's IS times R? 1.9 milliamps times 3.6 kilo ohms, whatever that happens to be. So the polarity of that voltage drop is going to be positive on the left-hand side of the resistor and negative on the right-hand side of the resistor. So if we wrote a Kirchhoff's voltage law loop starting at the ground of the non-inverting terminal, we would have the voltage drop over the resistor plus the output voltage is equal to 0, which means the output voltage is just negative the voltage drop over the resistor. Again, we could effectively do this in our head. If we look at the next problem, it's the exact same thing, except now we have to account for some non-zero voltage at the non-inverting input terminal, but the analysis is effectively the same. So it's going to wind up being V out is Vs minus the voltage drop over the resistor. So the voltage connected to the positive terminal is added and the voltage at the negative terminal is subtracted. That's why it's a non-inverting and an inverting input terminal. If we looked at the next problem, let's see. So what's the voltage drop over the resistor R1 have to be here if we apply the ideal op-amp rules? Nope. Consider that the current through the resistor R1 is flowing to the left. Where's it going to wind up going? It's 0, because it would flow into the input terminal and that can't happen. So that resistor R1 there is to distract you. So you would have negative V1 plus V2 plus V out is equal to 0, which means V out is V1 minus V2, I think here. I mean, this stuff is fair. Like I said, the problems that I put on the board were significantly more difficult than these. I like this guy because it's mean. What's the voltage drop over the resistor have to be? 0. So if we did a Kirchhoff's voltage law loop starting at ground on the non-inverting input terminal, we would have 0 plus V out is equal to 0, which means V out is equal to 0. This problem is another place to where we can just do Kirchhoff's voltage law, I believe, right? So negative V1 plus V2 plus V out is equal to 0. And then solve for V out. And then the last problem is the first one that actually requires even a little bit of analysis. So let's take a peek at this one real quick. What's the voltage present at the non-inverting input terminal? So what's the total voltage drop over the resistor R2? So, can you guys see my cursor on the screen or whatever? So we agree that this voltage is 0. So what's this voltage? So what's this voltage? So if this voltage is 0 and this voltage is 0, what's the voltage drop over the resistor R2? It's 0, right? So this resistor R2 doesn't do anything. So then it's just a very simple circuit with those two resistors to where you would apply Kirchhoff's current law at this node and find that the current flowing through the resistor R1 is the same as the current flowing through the resistor R3, and then solve for V out, which is what we did a couple of different times. All this stuff is fairly trivial. Like, you know, the in-class assignment problems are probably significantly harder than what I would put on the test with regards to op-amp circuits. So, any other questions? We got a lab on this stuff on Friday that kind of goes along with, so the next lecture is also on operational amplifiers, but it's on common op-amp topologies. And so all that means is like this circuit, you guys don't know this yet, but it is an example of an inverting op-amp, classic inverting op-amp case. And it has a very specific input-output relationship, which I derive in the video. Derive that for non-inverting op-amps, summers, even integrators and differentiators. But all of that it's all fine and dandy if you have to deal with op-amps a lot, but you can use the methods that we talked about today to solve literally any op-amp problem in this class without much particular effort. I'm not trying to discourage you from learning the differences between all the different op-amp forms, but having one method that works every time probably seems a little bit easier for most of you guys to digest. So, yeah, I don't know what else to talk about today. I'm very sorry I was muted. Thank you for mentioning something. So what I was saying is our basic operational amplifier is a 3-terminal device that has a non-inverting input terminal, an inverting input terminal, and an output terminal. Now, when we're dealing with ideal operational amplifier circuits, which are the only type of circuits we'll deal with here in ENGR 221, there are 2 basic rules that we'll be applying. The first says that there is no current flowing into or out of, so I guess that would be a better way to put it. The input terminals, which means by definition, this current must be 0 amps and this current must be 0 amps. Our second rule says that there can be no voltage drop between the input terminals. So that means that this voltage by definition is 0. And if we consider the voltage present at the inverting terminal with respect to ground, and the voltage present at the non-inverting input terminal with respect to ground, op-amp rule number 2 can be restated as simply the voltage present at the non-inverting input terminal must be equal to the voltage present at the inverting input terminal. So these are the 2 basic rules. Everything past this is just simply Ohm's law, Kirchhoff's current law, and Kirchhoff's voltage law. So let's take a look at a couple of examples. So let's say, see what's going on in chat. Okay. So let's say that we have the following circuit. excuse me, so this is our first circuit of interest. It may look a little complicated, but we'll see pretty shortly that our analysis is actually going to be fairly trivial. So if we apply rule number 1, we know that this current has to be 0 amps and this current has to be 0 amps. And applying rule number 2, whatever voltage we get here at the non-inverting input terminal has to be the exact same voltage we have present at the inverting input terminal. So our steps for analyzing these circuits are going to be really just 2 simple steps. Number 1 is to determine the value of the voltage present at the non-inverting input terminal. And then step number 2 is going to be to apply KCL at the inverting input. And if we can do these 2 steps properly, after having applied our ideal op-amp rules, we're going to get the output voltage correct every single time. So, who among you could suggest a way for us to determine the voltage V plus, the voltage with respect to ground present at the non-inverting input terminal? Multiple different ways to go about it. What did you suggest? Kirchhoff's voltage law. We can, but we need to recognize something else first. So let's go to this guy in pink. So there's going to be some current that's leaving that 6-volt source, right? And all of that current that's leaving the 6-volt source is then going to go flow down through the 15 kilo ohm resistor, because ideal op-amp rule 1 tells us that none of it can branch off and flow into the input terminal. Sure, yeah. So we could find the value of the current that I've set up in pink and then use Ohm's law. That's easy enough. What we could also do is recognize that since none of the current can branch off, from the perspective of the 6-volt source, it sees a simple voltage divider circuit, right? So we could say pretty easily that V plus is simply 6 volts multiplied by 15 kilo ohms, because we want the voltage drop with respect to ground. So we're finding the voltage drop over the resistor placed between ground and our node of interest. And our total series resistance seen by our source, which is a 10 kilo ohm resistor plus a 15 kilo ohm resistor. So 15 over 25 is 3 over 5, multiplied by 6 is, I think, 18 over 5 volts, which is 3.4. My math is right. 3.6, thank you. 3.6 volts. We could have also applied Kirchhoff's current law at the non-inverting input node and found the exact same result, just doing a little bit more math. We could treat it as a single loop circuit, find the current, and then use Ohm's law as was suggested. Any way that properly applies, or any way to find that voltage should work, as long as you're properly applying rule number 1 to note that no current is going to branch off. This voltage division method just happens to be the fastest. So that's the reason why I prefer it. So now that we know what that voltage V plus is, what we're going to do is add the currents leaving our inverting input terminal by using Kirchhoff's current law. So what is the voltage directed to the left through the 8 kilo ohm resistor going to be? So it'll be 3.6 volts divided by 8 kilo ohms, right? Just good old Ohm's law. What about the voltage going to the right through the 12 kilo ohm resistor? Exactly right. 3.6 minus V out over 12 kilo ohms is equal to 0. We have one equation, one unknown, so we can solve for it pretty easily. So that's going to be my math is correct. 9 volts. Take a moment to verify that. All righty, so one thing that I want to point out here is that our output resistance of 3 kilo ohms, did that show up in any of our equations? Did we use it anywhere? That's one of the really interesting things about at least the analysis of an ideal operational amplifier, is that the loading resistance doesn't really affect the behavior of the circuit at all. The only time it would be is if it were 0. So if you short out the output, then obviously the output voltage is going to be 0. But other than that, the output resistance doesn't particularly matter. Now in a practical op-amp circuit, so meaning a physically realized op-amp circuit, that's not remotely true, but we're just looking at an idealized case here. All right, so let's up the level of difficulty. Pretty much, yeah. And the reason why we don't really use mesh analysis effectively ever for op-amp circuits is because of the rules for the current. It kind of makes things a little messy. Yeah. So let's see. What can I do to make this mean? And let me make sure that that looks like a kilo ohm and not a capital M. All right, so this is a fairly ugly looking circuit. We're going to solve it in just the same way, and we're going to see that the analysis is pretty much just as easy. Applying op-amp rule number 1, we know that this current is 0 amps, and this current is 0 amps. And applying op-amp rule number 2, we know that this voltage V plus has to be identical to this voltage V minus. So how are we going to solve for the voltage V plus? Tell me how you would solve for V minus. Right, but you'd have one equation and 2 unknowns. So if we apply Kirchhoff's current law at the inverting input node, we would have an unknown voltage of V minus and an unknown voltage of V out.
I guess you just do -3 milliamps times 4 kiloohms.
For V plus?
For V plus.
That's correct. Yeah. Just using Ohm's law, right? Where we're noting that the current is flowing effectively up in this direction into the negative polarity terminal. So we would have V plus is equal to negative 3 milliamps times 4 kiloohms is equal to negative 12 volts. And now from this point, again, we just apply Kirchhoff's current law at the inverting input terminal. So we're going to be adding this current, and this current together, and that's going to allow us to find our output voltage V out. So what's the current flowing through the 1 kilo ohm resistor to the left going to be? Negative 12 volts over 1 kilo ohm. Okay. What's the current flowing to the left through the 6 kilo ohm resistor going to be? So it's not going to be negative 12 because there's that other voltage source there on the left-hand side, right? Negative 12 minus 2, thank you. What's the current flowing to the right through the 10 kilo ohm resistor? And now we can simply solve this guy for V out. Yep. So this is the method by which we solve operational amplifier circuits in this class. Fairly, in my opinion, fairly straightforward. I would argue that the problems that I give on the in-class assignment might actually be harder than what would show up on your test or what any of these are. Require a little bit more depth. I would also argue that the problems on the web work assignment are significantly easier than these problems, although we can easily take a look at them. So like if we look at the web work, let's see.
Is there a comprehensive exam or is just the last stuff?
It is comprehensive.
Oh, so it's all of the stuff, including stuff we haven't tested.
That is correct. Roughly 30% will be material from exam 1, 30% will be the material for exam 2, and 40% will be the remaining material. I don't particularly like that format because that means I have to spend a lot of time in circuits 2 reteaching student stuff, because how it generally works is students with good grades typically stop caring around after they get their grade back for exam 2, because they realize that if they're good with the exam 1 and exam 2 material, they can't really fail the last test, so they don't bother learning any of that stuff. Unfortunately, that stuff is very important when we get into circuits 2, so I have to spend like 2 weeks reteaching all that crap. But I don't really have a say in the matter. So let's look at the web work problems real quick, just to explain kind of how easy these things are going to be. So for this first problem, what is the voltage present at the non-inverting input terminal? Zero, because it's connected to ground. So that means if this voltage is 0, then this voltage right here is also 0, right? What's the voltage drop over that resistor? You don't need to give me a numerical value, just tell me how I'd figure it out. Right, so the current flowing from this source, all of it is going to flow through that resistor because none of it can branch off. So we could say that there is a voltage drop over the resistor, positive polarity on the left, negative polarity on the right, okay? If we did a Kirchhoff's voltage law equation, starting from ground here, we would have 0 volts plus 0 volts plus the voltage drop over the resistor plus the output voltage is equal to 0, which means V out is simply negative the voltage drop over the resistor. Trivial. If we look at our next problem, it's the exact same problem, except that now there's our voltage present at the non-inverting terminal isn't 0. So we'll find that V out is Vs minus the voltage drop over the resistor. Nothing particularly difficult there. If we look at this problem, maybe a little bit trickier. Who among you can tell me what the voltage drop over the resistor R1 is in this case? Mm-hmm. In problem 3. I disagree. Also disagree. How much current's flowing through it? No current can flow through it because of ideal op-amp rule number 1, which means the voltage drop over that resistor is 0. So that means V out is V1 minus V2. Yeah, so I mean, if you can apply those op-amp rules, op-amp rules 1 and 2, all of these problems are going to be terribly trivial. Let's look at this next guy here. Yeah, that's what I meant. V1 minus the one connected to the positive sign minus the one connected to the negative sign, whatever that was. So for this guy right here, what's the current flowing through the resistor? Still 0. So what's V out? Zero, right. So if we start here at the bottom and we do Kirchhoff's voltage law, we have 0 volts plus 0 volts plus 0 volts plus V out is equal to 0, which means V out is equal to 0. This guy right here should be fairly straightforward. What's V out going to be? Yep. This last one is the first one that's actually even remotely close to the level of difficulty of the questions that I would prefer to ask. What's the voltage present at the non-inverting input terminal? 0. So that means the voltage present at the inverting input terminal is also 0, right? What's the voltage drop over the resistor R2? It's 0, because 0 minus 0 is equal to 0. So that resistor R2 doesn't actually do anything there, right? So we have a situation to where we have a voltage source applying some current to this resistor R1. All that current flows through resistor R3, and that allows us to calculate V out. So in this case, it would actually be V out is negative R3 divided by R1 times Vs. You can do the algebra to prove that to yourself. All these op-amp problems are fairly trivial. You know, this first homework set involves applying the ideal op-amp rules and then really just writing a KVL equation for pretty much every one of them. The problems that I like to ask are more in line with the ones that we've discussed today and that you'll see on the old tests and stuff like that. And every single one of them can be solved by finding the voltage at the non-inverting input first, and then applying Kirchhoff's current law at the inverting input. That's how all negative feedback op-amp circuits can be. Not just taking it easy on you guys. I literally can't make it any more difficult than that. It cannot be done. No, it was negative R3 divided by R1 times Vs. Would you care for me to prove that? Sure. So we have the following circuit. Here's R1, here's R3, and we all agree that R2 wasn't doing anything, so that's why I'm not drawing. So this voltage here must be 0 volts because this voltage is 0 volts, right? This current has to equal this current, so we're going to have Vs divided by R1 is equal to negative V out divided by R3, which gives us V out is equal to negative R3 divided by R1 times Vs. This equation is just expressing that pink current in the two different ways because we know it has two different relationships. All of that pink current, or all of the current that's leaving our voltage source Vs has to flow up through that feedback resistor. None of it can branch off and flow into the input terminal. So this is actually the first circuit that I talk about in my next video lecture on common operational amplifier topographies. This is what's known as an inverting amplifier, and it always has this characteristic relationship. Negative feedback resistor over the input resistor multiplied by the input voltage. So, okay, so with that being said, the next lecture is going to be dealing with inverting amplifiers, non-inverting amplifiers, summing amplifiers, differencing amplifiers, integrating amplifiers, and differentiating amplifiers. I know that's a lot of different things. It's all based off a few basic topologies. And if you can memorize all of them, you can actually get away with solving an awful lot of op-amp circuits with doing zero circuit analysis whatsoever because they're very well behaved. That being said, you can still just use find the voltage at the non-inverting input terminal and then apply KCL at the inverting input terminal method and not have to memorize 6 different types of op-amp circuits. So it's really whichever way feels more comfortable to you. I'm not trying to discourage anybody from memorizing the different topologies, but the method that we talked about today is, in my opinion, pretty darn easy. All right, so I don't really have a whole heck of a lot else to talk about to you guys today, unless you just want me to make up more op-amp problems, and we'll use those 2 steps and solve it every time. So unless anybody has questions about the exam or anything, yes, ma'am. That is correct. Operational amplifiers will be pretty much the first topic on exam, well, not the first new topic on exam 3. So this will not be on the exam on Monday. Yes, ma'am. A review session? Yes, I will be doing a review session on Monday during class time on Zoom so that everybody can show up at the same time so that I don't have to do it twice. Yes, ma'am. Yeah, so it's because it's more op-amp stuff, and so you could approach in-class assignment number 17 by using the ideal op-amp, or no, excuse me, the identifying the type of amplifier and then working it that way, but it's the same thing. Op-amps are kind of too easy to keep throwing stuff at you. You're just going to get bored. In most textbooks, operational amplifiers are taught during the DC analysis section pretty early. I don't know why we teach them so late in this class, but we do. So maybe it's just because it's something light and breezy before we get into the horror that is complex numbers that you guys are going to be facing starting next week. So sorry, not really, but yeah. Yeah, no, I sup on your tears. Yeah. Any other questions? All right. Well, I guess we get out 20 minutes early because I don't have anything else to talk about really. If you have any questions about any of the homeworks or anything like that, feel free to shoot me an email.